Okay, so today what I wanted to do was to talk a little bit about dark matter because, in part because I recently got this lovely new dress which has from it a map of the dark matter in our universe that was put together from the BOSS experiment, the Baryon Oscillation Spectroscope Survey, from the Sloan Digital Sky Survey conducted out of the Apache Observatory in New Mexico, and Apache Point Observatory, sorry. And so this is a map of all the dark matter. What do we mean by dark matter? And this is going to be a general overview, and details may appear some other time. But this is the deal. So the big idea that we want to make sure we walk away with is this, what's already written on the board here. When we look at the motion of stars orbiting around the galaxy, how fast they move compared to where they are in the galaxy, how fast they move in their orbits, how strongly they're pulled towards the center of the galaxy around in their orbits. And when we look at how galaxies are pulled by each other and how that affects their motion, that requires a certain amount of mass to pull on them with gravity. So the mass that we see, that we know is there because of the motion, is the matter. However, when we go ahead and we look at all of our observations of those things, and we can see stars and gas and dust, and we know a lot of information about stars and gas and dust, and when we look at how much light is coming from those across the spectrum, we see that there's much more mass needed for the motion than what can be accounted for with the stuff that we see. And so, since we can't see all that mass, we can't see all that matter, it's dark matter. And again, this is including the entire spectrum, not just the light that our eyes can see, but the invisible parts of the spectrum as well. Radio, microwave, infrared, ultraviolet, X-ray, gamma ray, all that business too. So what's going on? How do we know that it's here? Well, let's take a look at how it would get connected to figuring out the amount of mass of something based on other things we observe. So we know that if you want something to change its velocity, such as turning, such as going around in an orbit, or speeding up or slowing down, we describe that relationship to a thing's mass through forces and through Newton's second law of motion. Newton's second law of motion, we could write it as acceleration is equal to the force acting on an object divided by the mass of the accelerated object. So the more mass a thing has, the less acceleration you're going to get with the same force. The more force you have, stronger the pull, the more acceleration you get, the more rapidly it changes its velocity, its speed or direction of motion, or both. So we have that. Now, when we look out at what are these forces that can act on galaxies and stars, there's a bunch of forces that exist. And they have to be among the forces that can work on things without directly touching. And the forces that we know are out there, we have the forces that act only on really tiny scales inside that are smaller or as small as the nucleus of an atom or smaller, nuclear forces. And so we're going to say, no, can't be those, too small of a scale. Electricity and magnetism, you may know that we have magnetic fields from the sun and from the planets, most of the planets, that extend way out into space. But our most distant spacecraft now have been passing around the edge of the region where that magnetic field, it shows its influence from our sun. The magnetic fields and electric fields tend to balance out over big distances because there's always the same number of north poles and south poles as each other. And so you have always a similar amount of pulling and pushing from the different magnets. And on average, there's equal amounts of positive and negative charge out there. And so you get all of those pushes and pulls from electricity balancing each other out as well. So that leaves us just with gravity. Gravity is the big force that gets to act on things over really big scales. And so that's our force. And so we know our modern understanding of gravity is best described by Einstein's general theory of relativity. However, an older version of gravity, the one that Isaac Newton worked out in the late 1600s, is a really good approximation, except under the most extreme circumstances, like right near a black hole or near a star, or you're talking about light passing by a particularly dense galaxy or something like that. So when you're looking at stars under normal circumstances, galaxies interacting with each other, we can work with Newton's laws here. The proper physicists and astrophysicists will work with the relativity as well, but let's work with Newton's laws here for a sec, because that is basically gets the same idea across. So, the force of gravity according to Newton's law of universal gravitation is equal to a constant, I'll call it the gravity constant, let me give a little more space here, sorry. Force of gravity equals gravity constant times the mass of the things doing the pulling times the mass of the thing accelerated divided by distance between the masses squared. And I'm writing it like, mass of the object that's pulling compared to the mass of the object that's being accelerated. We know that with forces, that you pull on one thing from one object, that second object is going to pull back on the first one. So we're talking gravity with stuff like, say, the Earth and the Moon. The Earth is pulling the Moon and making it turn around and go in orbit around the Earth. The Moon's also pulling back on the Earth just as strongly, and it makes it go in little tiny circles, relatively tiny circles, at the same number of orbits per year as the Moon does. The forces are the same size, but because the masses are different, the Earth's mass is much smaller, so its acceleration gets to be, the Earth's mass is much bigger, so its acceleration gets to be much smaller than the mass of the Moon. And that results in less motion, or less changing motion, less turning, a smaller radius for that turn. So we have these two rules together, and we can go ahead and plop the one into the other, substitute in, and let's see what happens. So if we take away the force of gravity here, and we put in instead, we're going to put the force of gravity into this equation. So all this stuff is going to go right in here, but then we're also going to have mass of the thing accelerated, and then that gets to equal the acceleration. And so, okay, so we see all these things, and the mass of the thing accelerated is both on the numerator and the denominator, so they can divide through, and to equal 1, they can cancel out. So we'll do that. Okay. And now to make some more space, I'm going to take that away. Okay. Well, what else do we have here? I was talking about how fast things go. And it turns out when things go around in orbits and they're turning, we can relate speed to the radius of the turn and to the acceleration that the thing has. So if we see how fast the thing is going, and we see how tight or how loose of a turn it is, we know the acceleration. So what does that look like, the equation? I may make another video to describe how it's derived, but it's equal to the speed squared divided by the radius of the turn. Well, if you're talking about stars going around a galaxy, or galaxies sort of orbiting around their own center of mass, that radius of the turn is basically the distance between those objects. The centers of masses of those objects. So if we're talking about, say, our sun going around our galaxy, that distance would be the distance from the sun to the center of the galaxy. The center of the galaxy is roughly uniform in mass, so the center of the galaxy is also about the same as the distance between the mass of the galaxy inside the orbit and the thing doing the orbiting. So we can put these together and say speed squared over radius of orbit is equal to all this stuff. We can say the distance between the masses is the radius of the orbit squared, and that the mass of the things pulling is the mass inside the orbit. So let's rework this equation so that we have the mass inside the orbit on one side, and we'll talk about the physical meaning of it. So radius of the orbit is on both sides in the denominator, but we've got 2 powers of it over here. So we can multiply both sides by that radius to cancel it out over here. So times radius over here, times radius over here. And those things cancel, so we're left like so. And then if we want to get mass inside the orbit all on its own, then we can multiply both sides by radius of the orbit, which basically is going to bring it over here. And divide both sides by that constant, which is going to bring it over to the denominator over here. And we get an equation that says that the mass inside of the orbit of a thing is related to the speed, square of the speed, and the distance, the radius of the orbit. That'll tell you how much mass is inside the thing. So that means that when we're looking at a galaxy, we can look at the stars near the center and going all the way out towards the edges, and up and down as well, and we can measure their speeds, and we can see how that speed changes, and then see how much mass is there. So let me rewrite this equation over here. and then I've been using words in my equations the whole time, so I will quickly rewrite this using algebraic symbols. We could say mass inside equals speed squared, tangential speed squared, times the radius divided by the gravity constant. Okay, so this is how we get our information. And you say, okay, well, how do we get that speed and that distance? There are a whole lot of ways that we can get distances to the different galaxies and stars. And a number of them rely on, I will need to do a whole other video on that. I can tell you that you use simple things like geometry, like measuring angles, like parallax. Like if you hold your thumb out from your face, you've got two different places where you can be looking at your thumb from, either eye. And so if you look at it with one eye, you'll see that it lines up with some spot in the background. And if you keep looking with your head pointed the same direction and shift which eye you're looking at your thumb with, it'll now line up with a different spot in the background. It'll have shifted a certain angle. And how big of a shift it is going to depend upon how close you held it to your face. We can use the geometry of that, the distance between the two places we observe from, and the distance between the places we observe from, and how much of an angle shift there is, to figure out what this distance is. There's a relationship between all those. We can use the distance between our two places we observe and the distance and the angle of the shift, the parallax shift, to figure out distances to nearby things. We've done that a whole bunch. And we've also looked at a whole bunch of different stars. And we can tell by the colors of the stars, they have various properties associated with them. When we look at all the different stars, we can tell what type of a star it is, how hot it is, how big it is, how massive it is, and we can use that information to say how much energy it's putting out. We can use it as what we call a standard candle. I'll write that down. If you have, say, a flashlight, or if we want to be more literal, a candle, and you look at it and it's like right up in your face, it's going to be very bright. The further away you bring it, the dimmer it appears to your eye. So something that would be blindingly light right up next to your face is going to be relatively dim if it's across the street or the other end of a football field or something from you. And there's a relationship from that. The amount of energy which goes to the brightness drops off with the square of the distance. We can use the amount of energy we collect from a star and how much energy we know it's putting out to say how far away it is. And we can do similar things with galaxies. There are a bunch of other objects that are further and further away that are very bright compared even to stars that we can use the similar tricks for. We know how bright they are, so we know how much energy is coming out from them, and we can use that to figure out distances. The furthest objects that we look for that can be seen, some of the brightest things that are in the universe are the light that comes out when there's a special type of supernova explosion. When a star dies and collapses and releases a whole bunch of light. Or rather, when a star has already stopped fusing and then more mass lands on it and it collapses into a neutron star and super explodes in supernova. Those we can see, we can detect some of those billions of light years away. So we get distances like that. If we know the distance to the thing, like the distance to your thumb, and you know the angle that it was taking up, you can use the same geometry we use for parallax to see how wide the thing is. It's all about triangles. These all have relationships to each other from geometry or trigonometry. So it doesn't matter if on the D side these are two places where you're observing some distant object, and this is the angle that you see it shifting to figure out how far away it is, or if you found out how far away it is from standard candles, measured the angle, say, from its center to a star you're trying to find speed information about, and then use that to find the distance that that star is from the center. So we use that sort of thing to find distances. Speeds, we use the Doppler effect. And that one I'm really going to need to do a full other video on. But the essence with that is that every object that's glowing, every object glows. We, as human beings, glow in the infrared part of the spectrum. It's beyond the red end of the spectrum. The dark background of the universe, left over from the Big Bang, glows in the radio part of the spectrum. The stars are all glowing, have a big part of where they glow in the visible light part of the spectrum, but the blue stars are actually even brighter in the ultraviolet part. When you look at those stars, or any object, and you split the colors of light that come through it into a spectrum, like with a prism, or a diffraction grating, if you're familiar with those, then you wind up seeing in the spectrum different lines, and they go along with very specific wavelengths or frequencies. Let's say wavelength. And so here is red, and here is violet, and blue. Now there's lots of different stripes that can go along with different reds and whatnot, and you have these in the invisible parts of the spectrum too. But each element and each molecule makes their own distinct pattern of these lines. And so if we know something that affects the wavelength, we could use those as a reference. And speed affects the wavelength and the frequency of those lines. The Doppler shift is the shift in frequency of waves based upon how fast the thing experiencing the wave and the thing making the wave, the source and the experiencer being the receiver, the thing making it being the source, how fast they're moving compared to each other. If you make waves and imagine that you're tapping on the surface of a pond or a pool of water, then if you keep tapping here in the middle, the wave fronts will go out, and we're going to pretend that those are a bunch of concentric circles, that they're all, so that the distance in between them is staying the same. And the distance between the peaks of the ripples, we're going to call those the wavelength. And light has wavelengths too. It's long on the red part of the spectrum, it's short on the violet part of the spectrum. But imagine if this thing is moving. If this thing is moving, if where you tap, you slowly move towards the right of the board, then if that first wave left from where we were, and then, let's not quite go that fast, and then the second wave was, instead of being centered here, was centered over here. Let's even color code it. And let's throw in a third wave. And the third wave is centered over here. You see that the wavelengths get bunched together on the side where, in the direction where the thing is moving to. And they get spread apart on the side where the thing is moving away from. And it's this shift in wavelength or frequency. Frequency would be how fast they move past a thing, how many of them go past a particular point per time. That difference related to the speed of the source is the Doppler shift. We experience this with sound waves all the time. When you have a car pass you by, if its engine, when it was parked and idling, or you rev it while it's at rest, sounds like, well, when it's coming towards you, it'll have a higher pitch, like, and then after it passes you, it'll have a lower pitch. So, you're at a racetrack and the car goes zipping by you. It has that shift in tone where it goes as it goes by. Or like the klaxons of, some emergency vehicle could go da 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 as they pass you. The same thing happens with light. All of those wavelengths of all those lines that I was talking about before, they move based upon how we're moving relative to them. If the thing is coming close to us, the wavelength of this is going to get shorter and the frequency is going to get higher. So if something was in the, say, a green color light, it would get shifted more towards the violet end of the spectrum. We see blue in our eyes a little better than violet, so we call that blue shifting. if the thing is going away from us, it stretches out those wavelengths, it makes them longer, and it makes the frequency that they pass by us lower. So if you had a line, again, in the green part of the spectrum, it would be shifted towards in the direction of the red part of the spectrum. And so we call that a redshift. And how big of a shift it is tells us how big the speed is. And so we use that to figure out our speeds. So we can figure out speeds, we can figure out distances, we can figure out the mass inside of the orbits. Well, that's how you figure out the mass, but then we go back to the original statement. You figure out that mass, and you say, okay, I know all of this information about all the stars that are in there. I can tell what sorts of stars are there and how many of them there are based on how much light we see, standard candle. We can make observations about the amount of dust and gas and other ordinary matter that we can see across the whole spectrum. It doesn't have to be just in the visible part of the spectrum. It can be infrared, radio, microwave, can be ultraviolet, X-ray, gamma ray. We look across the whole thing and we see from the whole spectrum of the object how much mass is coming from the stuff that we know about. And it turns out that that ordinary matter only accounts for about only accounts for about 1/7 or 1/6 of total mass. There's a bunch of mass out there missing, and we figured out that it can't be stuff that's made from regular matter. Like you might think, oh, well, I mean, what if it's just really dim? There's stuff out there that could be really dim. Stuff like brown dwarfs. Those are things that are not quite big enough to be a star, not quite big enough for their gravity to smush them all together enough to get fusion started in sustaining in their centers, but pretty darn close, enough that they're still kind of glowing from their own heat from the gravity collapse a little bit in a really dull dim red, brown dwarfs. But we do surveys and we see, no, we've done special careful checks. And we see, no, it can't be brown dwarfs, nowhere near enough mass from how many brown dwarfs there could be out there. What about black holes? Well, it turns out, black holes, we can see evidence of black holes in a variety of ways, and there's not enough black holes out there that would be like truly black and not get brightened up from stuff falling towards them and speeding up and heating up, that they're not enough either. Black holes that come from dead stars. And so we have to come up with other ideas about what is this dark matter. And so right now we're thinking it's got to be stuff that isn't even made up of stuff like protons and electrons and neutrons, or the quarks that make up those protons and electrons, or protons and neutrons rather, or the neutrinos that go along with those electrons, or the slightly heavier versions of those things out there that we can make in laboratories, or very energetic things in space can make, that don't last very long. None of those things work. But we think it's got to be made up of some other type of particle that we just haven't been able to observe in the lab yet. And it's no wonder, because it only interacts the way that we have been able to see is through gravity. And gravity is really weak compared to the other forces. It is hard to measure on the scale of even one human to another human, the pull of gravity. And if you're talking about subatomic particles, things that have masses that are, around 10 to the minus 27 times smaller than a liter of water for mass, that's you're out of luck looking for it from gravity on scales that small. So it's a really interesting area of active research. There's some suspicion that some of these particles could be things that we might be able to see by whacking more stuff together at super high speeds, like we do in the accelerator experiments, like the Large Hadron Collider at CERN near Geneva, Switzerland. And we have a whole bunch of other accelerators like that, like the one north of Chicago at Fermilab. But there's a variety of these things spread around the world. Those are just a couple of the biggest ones. So maybe we'll find evidence that way. But it's a really cool and interesting question that's been an active puzzle in astronomy and physics for decades. That's it.